Okay. In addition to molarity, like molarity was pretty simple, right? It was all about just concentration, how strong something tastes, how strong something is. Like even like I have to deal with like these like it's like these tiny gnats in my house plants, and right now, they say to use like hydrogen peroxide, but it's too strong. Straight up hydrogen peroxide is way too strong, so they say to dilute it 1 part hydrogen peroxide, 4 part water. So that's dilution. So a part of this whole concentration, how strong something is, if something's too strong, you have to dilute it, right? And so there's a dilution equation. M1V1 equals M2V2. This is dilution. Okay. Now, we can do problems with molarity and dilution, but then I kind of want to just go over like acids and bases, right? That exam I think people struggled a lot with, so we can break down like that one of the exams, okay? So acids and bases, we're looking at those crazy equations, right? pH plus POH equals 14. And I really suggest you look at your the equation sheet. So look at your equation sheet and be able to really see what's there. But it has all these. pH plus POH equals 14. It has pH equals negative log of H plus concentration. POH is equal to negative log of OH minus concentration, right? And the two that it doesn't have, the two equations that are not there, and ones that you need to remember off the top of your head, is 10 to the negative pH power is H plus concentration, right? These two are on your equation sheet. I think there's a couple other ones on your equation sheet too. They have like H plus times OH minus is always equal to 1 times 10 to the negative 14. This is also known as KW, the constant for water. The equilibrium constant for water is H plus times OH minus equal always 1 times 10 to the negative 14 power. I think that's all in your equation sheet. But the other one that's not there is OH minus here is 10 to the negative POH power. So those two I don't think are found anywhere on your equation sheet, but they're pretty important, crucial to, if they give you the pH, to get H plus. Okay? All right, so those are the main equations for the acids and base. I'm going to open up I'm going straight to like your straight to your exam here. And let's churn out some of these questions, and then probably last hour self-study or something, right? But let's try to get through as many as we can here. Maybe open with Cami would be better. Do you remember this test? It was kind of difficult, right? Those 10 questions, each one was 10 points. I think I curved this test for y'all because it was too intense. You guys, some of you did really poorly, right? It's not multiple choice. It was all like fill in. It was all or nothing. Okay, so a question like number one question like number 1, what is the pH of 0.320 molarity solution of a strong acid, right? Sometimes I won't even say it's a strong acid, but you know, what tells me it's strong right away is that they don't mention anything about Ka. You know, the acid dissociation constant. If they don't mention Ka in the problem at all, like solve for the Ka or here's the Ka, if they don't talk about that, it's automatically in my mind strong. They're not saying Ka because it's strong. It is a strong acid. Nitric acid is very strong. I showed one of my periods, and if we have time, if the fume hood starts working again, I'll show you. But it'll disintegrate a penny. So I put a penny in nitric acid, and within 5 minutes, penny was gone. So this stuff is strong. So you know what this number means? This number 0.320, because nitric acid looks like this, right? And it's gonna break apart 100% into this and this, 100%. So all of this, which is the starting material, all of it's gonna break apart into H plus and NO3 minus. So it's gonna, if you start with 0.320 molarity of HNO3, you pretty much end up with 0.320 molarity H plus. It is the H plus. That number is the H plus because 100% of HNO3 is going to break apart into H plus and NO3 minus. It's also the NO3 minus, right? If you had 1 million of those HNO3s, you end up with 1 million H pluses and 1 million NO3 minuses. So if you start with 0.320 molarity, you end up with 0.320 molarity. So if this is the H plus, right? If that is the H plus, then you can solve for the pH. You just negative log the H plus, right? So you negative log 0.320 in your calculators, and you're done with that problem. Okay, so that's what you have to do for a problem like that. And I got the pH is 0.495. Remember, pH, anything under 7 is an acid. So this is a pretty strong acid, right? pH is super low. It's almost like battery acid. What if you had H2SO4 though? It's also a strong acid. And they give you this molarity, let's say, and they're asking you for the pH. This is a tricky one. I didn't give you a tricky one on the test, but maybe on the final, who knows? I don't know. But H2SO4, if it's at H2SO4, it's still strong. The thing about H2SO4 is because there's 2 hydrogens, it's going to create 2 H pluses for every H2SO4. It's going to create 1 SO4 minus. So you know what happens to this value here? You got to double it. Over here on the right, it's going to be 0.640. This still, the SO4 2 minus is still 0.320. So this number is what you're going to use. You're going to use the 0.640 molarity as your H plus. So you negative log 0.640 to get the pH. So very tricky. Whenever you see H2SO4 or like Ca, like the bases, sometimes it's Ca parentheses OH, close parentheses with a 2 outside, and they don't say it's Kb problem, then that means it's a strong base. That's gonna create 2 OH minuses for every one of them. Okay? All right. Okay, number 2. Calculate the Ka of a 0.2 molarity solution of propionic acid with a pH of 4.88. So I mean, I don't like to just jump to this, but I will. But I hope you know why it ends up like x squared. Maybe you don't at this point. You just know to use it. Remember, it's always going to be x squared. The bottom is going to be the original concentration, which is 0.20 0.2 molarity minus x or whatever. And usually, most of the time, you can just get rid of this x, so that's nice, right? And then what you need pretty much to solve for Ka is you need the x, right? If you have the x here, you can solve for the Ka. So what the heck is the x? The x is the H plus. X is H plus, right? I hate jumping to this because really you need to know what's going on, but this is how you do it. This is like the shortcut. Because remember how I showed you how to, like the whole ice box? Initial change equilibrium, and I put like, oh, this is how much, and you have none of this stuff, and then at change, minus x plus x plus x. And then at equilibrium, that's how you got x squared over, 0.2 minus x. So what other information do you have, right? They give you 4.88, yeah.
So if you want to be plus in this situation, you want to take 4.88 and it's 10 to the negative 4.88.
10 to the negative 4.88, right? So if you put 10 to the negative 4.88 power, that's going to give you H plus. That is x. Okay, so if you solve right there, you have x and you plug it in for x in the numerator. Usually the denominator x you can ignore. You should check it though. So let's go all the way to the end. 10, right? 10 to the negative 4.88. And that's H plus. I'm going to square that and divide it by 0.2. And my final answer, I have Ka equaling 8.69 times 10 to the negative 10 power. That's the final answer. Now, in order to be certain you don't have to use quadratic, I think one of these questions you ended up having to, but I just threw it out. Like, I just didn't, But you really should check this. And sometimes I'll ask you, like, what's the percent ionization? You have to check the percent ionization. And that equals to, like, how much of x, right? Which I lost x because I was just plugging everything in the calculator. So x, which is H plus, is equal to 0.000013182. So the question is, how much of that, like, is that small enough to ignore, is the question, in the denominator. The denominator is 0.2 minus that. That's such a small number, I think I'm good to go. It just needs to be less than 5% of 0.2. If it's less than 5% of your original molarity, you can ignore x in the denominator. So how do you solve whether it's less than 5%? Well, you got to compare this number, right? How much ionized here over how much you started with. You started with 0.2. You started with 0.2. You only 0.000013182 changed. Switched over. Only that amount switched over. So I want to know what percent is ionized. The percent ionized times 100. So divided by 0.2 times 100, and I get 0.00659%. That's way below 5%. If it's not less than 5%, you do have to do quadratic equation. Maybe on the final, the question would be, one of the answer choices would be like, would need to use quadratic equation. That would be a pretty tricky one. But then you now know, and I hope the rest of the kids that are not here will know. But you know what I mean? So if you check this and it's over 5% and an answer choice says you need to use quadratic equation for this problem, you can just choose that as your answer choice. I don't know. Maybe. Okay? All right. Number 3, I'm going to, yeah.
Can you show us how to use quadratic to solve it?
I can, but it's gonna be. I'll do it next time, or, like I said, I'm not gonna have you. I'm not gonna have you have to do it on the test, on the final. If you have to use quadratic, the answer choice, one of the answer choices will say, I need to use I would need to use quadratic equation for this problem. But I don't know how to use quadratic equation or something, you know? So that'll just be your answer. So you won't ever have to do it.
So we don't actually
But
solve this.
you won't have to solve it. Once you test it and once you know it's more than 5%, if you test it, because some students are not going to test it. They're just going to, and the answer choice will be there. Them ignoring that x in the denominator when they shouldn't. And then the answer choice will be there and they'll bubble that thinking, you know, they got it right. But in actuality, they should have chosen E for you need to use quadratic equation, and we don't know how to use quadratic equation or something. But just knowing that part is most of the problem, you know? Number 3, I'm going to skip. I want you to try doing it. You know, it's CaOH2. They don't talk about Kb at all. So this must be a strong base, right? It must be a strong base. And don't forget, it says OH with a 2 outside. So it's going to create 2 OH minuses. For every one of those, it's going to create 2 OH minuses. So you do that on your own. Let's go to number 4. All right, so number 4. So 4.35 grams dissolved in 2 liters of water is found to be the H plus. They gave me the H plus. Calculate Ka. This is kind of easy too. Again, it's just it breaks down to this over and over, right? This whole test just broke down to Ka equal x squared. They gave us the x, which is good, but they don't give us something else, you know? Yeah, they don't give us the original molarity. So, do you know what to do or no? So this is what your mind has to realize is, wait, they gave me grams, they gave me liters, and then you have to think like, oh, I need molarity. I need the original concentration of the acid. And so this was like a combination between molarity, the unit before, and acids and bases. You got to use this equation. Because you have grams, you can change that to moles. And you have liters. So liters is 2. And 4.35, you can divide that by the molar mass of HC6H5CO2. Okay, and I got like 0.035617784, something like that. My molar masses might be a little bit different, but hopefully it's similar. 0.0178 molarity. Can you check that? I don't know. It's probably right. Anyways, percent ionization, I calculated this also, is 5.34%. You cannot ignore that X in the denominator, you know? But luckily, we don't have to this time around. Because they gave you the X, you know, if they give you the X, you need to plug it in both here and here. Plug it in both. Don't lose that X in the denominator. If you're given the X and you're asked for Ka, do not ignore that minus X in the denominator because you have X. So plug it in at the top and bottom and use this as molarity because we solved for it. Grams to moles and then divide it by liters. Now you have all the numbers and you solve for Ka. Okay, so that's how you do that one. Oh, number 5 was pretty tricky, right? Let's do number 5 real quick, see if we can do it. Okay, so what is the pH of a solution formed when you have 20 milliliters, 0.25 molarity, this is CaOH2, and 10 milliliters, 0.4 molarity, HCl. This is called a neutralization problem. We did several of them. They're gonna neutralize each other. We have a strong base and a strong acid, and they're gonna knock each other out until one of them wins. And then whichever one wins, you have to find out how much of whatever one is left over. And that is gonna be the determining factor of what the pH is. Whoever wins out, and by how much by. And then whatever's left over, that OH minus or H plus, you negative log and get pH. Remember, if you end up with the base winning, if you negative log that, that's POH. You have to subtract from 14 to get the final pH. So the tricky thing about this one was that this is OH with a 2. So it's going to create 2 OH minuses, right? CaOH2 is going to create Ca2 plus, but 2 OH minuses. So the concentration, like 0.25 molarity, I believe it's going to end up being 0.5 molarity. Please stop me if it's not I'm doing something wrong, but now you know the equation molarity equals moles over liter. Well, molarity also equals millimoles over milliliter. Millimoles over milliliter. So look what you can do. If you multiply, if molarity times milliliter will equal millimole. You don't have to use millimole. You can use moles if you want. That all that means is you have to change these milliliters to liters. Then plug it in right here and get molarity. Plug it in right here, multiply by molarity to get moles. But do you see this? Molarity times milliliter is equal to your millimole. I'm going to straight up change this to 0.5 molarity so I make sure. So this times this and this times this are going to be your millimoles of OH minus and H plus. All right, so 20 times 0.5. The first one here, 10 millimoles. This is OH minus. The second one, 10 times 0.4. 4 millimoles of H plus. Yeah, I think these problems were the hardest ones of the test. So who won? You have 10 millimoles of OH minus, right? So OH minus wins, right? Winner. And it won by 6 millimoles. So, they're going to knock each other out, It's a neutralization. So you end up with 6 millimoles left over. Now, molarity, remember, is millimoles, let's say, over milliliter. And to find, because you need to find molarity of OH minus, so you can negative log it to get POH, and then subtract from 14 to get pH. This problem was very hard. So what do you have to do? Molarity equals 6 left over. Now milliliter is now total milliliters, because you combine the two right now. Right? So it's 30 milliliters. It's 20 plus 10. You've added the two together. It's 30 milliliter. Right? 6 over 30. So molarity is 0.2. This is OH minus. Right? Negative log 0.2. But that's the POH, okay? Because you're negative logging the OH minus. So negative log 0.2. And you're getting 0.69897. 14 minus that answer. This is POH. So the pH is equal to 13.3. Answer kind of makes sense. The base did win. If I did it right, the base won, and so the pH should be over 7 for sure. Over 7, remember, is a base. Under 7 is acid. Yep.
Go back to number 4.
Number 4? What about it?
Can you go back to this like computer, please? Still not like very popular definition.
Yeah, I'll go back after. Let me finish real quick.
Of course.
Yeah, we have plenty of time. I'm gonna keep going and just finish real quick, and then. All right. Which next question would you like me to do?
Number 10.
Number 10? Okay. Number 10. Pretty good question. There's like two more. There's one more question I want to try too. This is a pretty difficult test, huh? But you had it in you. If you're watching me right now, right? Kind of like, is it helpful? Number 10. The pH of a solution that contains this nitrous acid and acetic acid. There's two sources of acid. So if you can find the H plus, right? The contribution of H plus by both of these acids and add up the H pluses together, that would be the total H plus concentration. If you negative log H plus, that's the pH. So, they gave you Ka, they gave you this. So, I think what they want you to do is just simply do two separate problems and just add up the H pluses together. So, equals x squared over 0.325 and solve for x. And then separately, I would go 1.8 times 10 to the negative 5 equals x squared over 0.139. Solve for x and x. Once you solve for the two x's, that's the H plus. That the first x is the H plus nitrous acid gave. The second x is the H plus that acetic acid contributed. Add both of their contributions of H pluses together, and then negative log that to get the pH. For this, for the purple, I'm getting x equals 0.01209. For the next one, I got x equals 0.001581771. Add the two together. Like total, I'm getting 0.013671771. Again, I could be making mistakes. I'm not checking my work. I'm just plugging in for the first time. I hope it's right. And then you add the two x's together, which is that right here. That's the H plus now. H plus total. Negative log and you get pH equals 1.86.
Mr. Kim, so what was the answer for number 10?
1.86. Is it wrong?
We didn't see what you put.
Yeah.
How did you combine that?
I want you to try number 7 on your own. It looks like a pretty challenging one, but you should be able to do a question like number 7. I'm recording this whole thing, I think. So I don't know if it's going to work, and then maybe I can upload it. So that the whole other period, and hopefully they're recording my voice too. I have no idea. And then if I can upload this on YouTube or something, you guys can watch it. You know? Number 7, write the equation for the dissociation of calcium hydroxide. So we're looking at calcium hydroxide. The dissociation is going to look like this: Ca2 plus and 2 OH minuses, okay? That's how you do it. The coefficient becomes 2 OH minuses. So that's how you do the equation for the dissociation. If the pH is 11.64 and you have a 2.55 liter solution, how many moles of calcium hydroxide are in the solution? They want this, and they want moles. So what do you need to do? This is pH. Oh, and you have 2.55 liters of solution. That's the pH. Now, you know what I can do to the pH? I can change it to the POH, and you know what I can do with the POH? I can change it to the OH minus. That's the crucial thought process you had to have. If not, you would just be done with this problem and got a 0. A lot of students just stared at this and they didn't know where to go. You have to just start with what they give you and just really think about how can you transform that into something that's useful. They gave you pH for a reason. They give you liters for a reason too, but that's for later when you're trying to get moles, I would think. And so pH is 11.64, and I'm like, wait, this is a base though. Okay, well, you can change pH to POH, then to OH minus, which then could help you put it in here somewhere. So let's do that. 11.64, 14 minus, right? 14 minus 11.64. And then 10 to the negative of that to get OH minus. But here's the thing. If you have that much OH minus, which is this, right? If you have that much OH minus, you're going to get half of that of CaOH2. If you have that much OH minus, you actually started off with half of that of calcium hydroxide. That's another crucial step that if you don't realize, there's no way you can find the correct answer. You could have gone all the way to solving for OH minus, but because you realize you have to see how that there's 2 OH minuses for every 1 CaOH2. That means that this molarity of OH minus, you started with half that in CaOH2 because CaOH2 gave 2 OH minuses for every one of them. So you started with only half that in the original. So you have to divide by 2. Or this kind of spills into stoichiometry, mole ratio. You need to use this and you write the mole ratio train to the front, which is 1 over 2. Where you're going is a 1, you came from a 2. So it's divide by 2. So you got to divide by 2. And you end up with 0.002182579, whatever, molarity. This is CaOH2. They want to know moles, though. Molarity equals moles over liter. So molarity times liter equals moles. So this times 2.55, that's in the problem, 2.55 liters will give you moles. So times 2.55. Right? Final answer 0.00557 or something moles. I think I remember an answer like that. I'm not sure though. It looks a little off. So I don't know if I pressed the one number wrong or something somewhere. No. Do you know if that's the answer? Correct. Yeah, you already know that it is? From like an answer key or something? Amazing. So that's the final answer and you have to do all that. So pH, change to POH, go to OH minus. That is OH minus. Okay, that's great, but you're going to start with half of that in CaOH2. They wanted moles of CaOH2. So you're going to start with half of that and then multiply it by 2.55 liters. Okay. That's it.